Modern agriculture is marketed as a triumph of control. Bigger machines, smarter software, predictive models that promise certainty in an uncertain world. From the outside, the system looks calm, optimized, almost inevitable. Fields align in perfect geometry. Harvest schedules are calculated months in advance. Inputs arrive on time, just in time, every time. The narrative suggests permanence. That narrative is fragile. Agriculture today does not collapse slowly. It fails suddenly, not because crops forget how to grow, but because the systems supporting them are layered so tightly that one fracture cascades into many. When a country experiences an abrupt disruption, the farm does not respond emotionally or ideologically. It responds mechanically. Fuel deliveries miss a window. Fertilizer shipments stall. Data access degrades. A planting decision becomes a guess. At that moment, agriculture reveals its true nature. It is not resilient by default. It is conditional. This documentary is not about politics, leadership, or blame. Those discussions dominate headlines but explain very little about what actually happens on the ground. This is about systems. Food production is a conversion process. Inputs become calories through time-sensitive, energy-dependent operations. When the system is intact, the conversion looks effortless. When it breaks, the consequences are immediate, measurable, and unforgiving. The farm is where abstraction ends. Financial markets can pause. Governments can negotiate. Media can argue. Crops cannot. Seasons do not extend deadlines. Soil temperature does not care about statements. Rain does not reschedule itself to accommodate logistics failures. Agriculture operates on biological clocks layered on top of industrial ones. When those clocks fall out of sync, yield disappears. The illusion of stability is strongest right before failure. Modern agriculture often points to record yields as proof of resilience. But high output is not resilience. It is performance under ideal conditions. True resilience is measured under stress, when inputs are late, energy is scarce, and information is incomplete. By that definition, many modern food systems are optimized for speed, not survival. What makes sudden disruption so dangerous is not the scale of the initial shock. It is the speed. Highly optimized systems are efficient precisely because they have removed redundancy. Inventory is minimized, buffers are eliminated, slack is treated as waste. This works beautifully when everything functions. When it does not, the system has nowhere to absorb impact. On a farm, this means decisions must be made with partial information. Do you plant without guaranteed fertilizer supply? Do you harvest without confirmed transport? Do you burn limited fuel now or save it for later operations that may never come? These are not theoretical questions. They are operational dilemmas that appear within days of systemic disruption. From the outside, food shortages look like sudden events. Shelves empty, prices spike, panic spreads, but these outcomes are downstream effects. The real failure occurs earlier, quietly, at the input level. When diesel does not arrive, when spare parts are unavailable, when digital systems that guide precision equipment lose reliability. By the time consumers notice, the damage is already locked into the season. Agriculture is often described as traditional, even primitive. In reality, it is one of the most complex industrial systems in existence. It integrates biology, chemistry, mechanics, logistics, and data into a narrow seasonal window. Complexity increases output, but it also increases points of failure. Each additional dependency is another potential fracture. This is why sudden national-level disruptions hit food systems so hard. Not because farmers lack skill or effort, but because the system they operate within assumes continuity. It assumes fuel stations stay open. It assumes borders function. It assumes digital infrastructure remains stable. These assumptions are rarely questioned until they fail. When disruption arrives, agriculture does not get time to adapt gradually. There is no slow ramp down. Fields are either planted or they are not. Crops are either harvested or they rot. Food production is binary at critical moments. The system either completes the chain or it breaks. Understanding this changes how we interpret crisis. Food systems are not passive victims of external shocks. They are amplifiers. Small disruptions upstream create outsized effects downstream because of timing, scale, and biological constraints. A delayed input today is not a minor inconvenience. It is a yield reduction months from now. This first section establishes a simple reality. Modern agriculture is powerful, but not invincible. Its strength depends on invisible systems functioning continuously. When those systems fracture suddenly, farms feel it first, long before cities understand what is happening. The rest of this documentary will examine those systems layer by layer. Fuel, fertilizers, data, logistics, technology, not to assign blame, but to expose dependencies. Because the future of food will not be decided by narratives. It will be decided by whether these systems are designed to survive disruption, not just perform in perfect conditions. For most of human history, farming was local by necessity. Inputs were produced nearby, knowledge was passed down directly. Failure was visible, contained, and usually seasonal. Modern agriculture inverted that model completely. Today, a single field may depend on inputs sourced from multiple continents, financed through global markets, guided by satellites orbiting the planet, and optimized by software written thousands of kilometers away. This transformation delivered unprecedented productivity. Yields rose, labor requirements fell, food became cheaper and more abundant. But this efficiency came with a trade-off that is rarely acknowledged. The farm stopped being an independent system and became a terminal node in a global network. When that network functions smoothly, the farm appears powerful. When it does not, the farm becomes exposed. Isolation is no longer a realistic option for most large-scale operations. Seeds are proprietary, fertilizers are industrial, machinery requires specialized parts and diagnostics. Even basic agronomic decisions are often shaped by external data streams. The modern farm does not merely interact with the global system, it is embedded inside it. This embeddedness changes the nature of risk. Local weather is no longer the dominant threat. Systemic disruption is. Border closures, financial freezes, transportation bottlenecks, energy shortages. These are not agricultural events, yet they dictate agricultural outcomes. The more integrated the system, the less visible its dependencies become. Farmers may see a seed brand, but not the chemical plants behind it. They may see fertilizer pricing, but not the energy infrastructure required to produce it. They may rely on GPS guidance daily without considering the geopolitical and technical systems that keep that signal precise. This invisibility creates false confidence. When systems work consistently, they are assumed to be permanent. Contracts replace contingency plans. Inventory levels are optimized downward. Redundancy is labeled inefficiency. The system becomes lean, but also brittle. In highly integrated agriculture, failure rarely originates on the farm. It arrives from outside: a delayed shipment, a payment system interruption, a logistics breakdown hundreds of kilometers away. By the time the effect reaches the field, the cause is often impossible to influence. This is why modern disruptions feel unfair to producers. Farmers can do everything right agronomically and still lose a season due to forces entirely beyond their control. The system rewards precision but punishes dependence. Global integration also synchronizes failure. When many farms rely on the same suppliers, platforms, and logistics corridors, a single disruption affects thousands of operations simultaneously. Local adaptation becomes harder because alternatives are scarce or equally constrained. In the past, agricultural failure was often uneven. One region suffered while another compensated. Today, system-level disruptions reduce that buffering effect. If everyone sources fertilizer from the same global chain, everyone feels the shock at the same time. This interconnectedness extends to finance. Input credit, futures contracts, insurance models. Financial systems assume continuity just as physical systems do. When continuity breaks, liquidity evaporates precisely when farmers need it most. The result is a paradox. Modern agriculture is globally connected, yet locally vulnerable. It produces more than ever, yet tolerates disruption less than at any point in history. Understanding this is critical. The problem is not globalization itself. The problem is unexamined dependence. Systems designed only for efficiency create hidden single points of failure. When those points break, isolation is impossible because the system removed the tools required to operate independently. Agriculture did not become fragile because farmers modernized. It became fragile because modernization prioritized optimization over resilience. The assumption was that the network would always be there. When it is not, farms discover how little control they truly have. This section establishes a central truth: modern agriculture does not fail alone. It fails together, and when a globally integrated system stumbles, the shock travels faster than adaptation. In the next section, we examine the most immediate and unforgiving dependency of all: energy. Because before food moves, fuel must flow. Every modern food system is, at its core, an energy system. Calories do not reach people by biology alone. They are pushed, lifted, processed, cooled, transported, and stored by machines. Machines do not operate on intention or planning. They operate on fuel. When energy flow is interrupted, agriculture does not slow down gracefully. It stops. Fuel is the first dependency to reveal failure because it underpins every other operation. Tractors do not plant without diesel. Harvesters do not run on optimism. Irrigation pumps do not respond to speeches. Even farms that appear low-tech are embedded in an energy-intensive chain. The fertilizer applied to the field was manufactured using large amounts of natural gas. The seed was processed, packaged, and transported using fuel. Energy is present long before the engine turns on in the field. When fuel supply becomes uncertain, farms immediately shift priorities. Yield maximization is abandoned. The goal becomes operational survival. Decisions are no longer about what produces the most, but about what consumes the least. Fields may be partially planted. Secondary operations are postponed or cancelled entirely. Marginal land is ignored because it cannot justify the fuel cost. Unlike many inputs, fuel disruption has no delay buffer. Fertilizer shortages may reveal themselves months later at harvest. Fuel shortages are visible within days. Equipment sits idle. Schedules collapse. Labor waits without purpose. Biological timing continues while mechanical capacity disappears. This creates a brutal asymmetry. Crops continue to develop according to temperature and moisture. Weeds do not pause. Pests do not reschedule. The biological clock keeps running while the industrial clock stops. Yield loss becomes inevitable, not because of agronomic mistakes, but because energy was unavailable at the critical moment. Fuel scarcity also reshapes logistics immediately. Transport becomes the limiting factor. Grain can be harvested but not moved. Inputs may exist in warehouses but cannot reach the field. The physical distance between nodes in the food system suddenly matters again. What was once trivial becomes decisive. In many modern systems, fuel access is assumed rather than secured. On-farm storage is minimal. Supply contracts rely on external distributors. This is efficient in stable conditions, but catastrophic under disruption. When fuel stations close or ration supply, agriculture competes with emergency services, transport, and industry. Farms are rarely prioritized. The irony is that agriculture produces the most essential output of all, yet it is treated as a secondary energy consumer. Food security depends on energy security, but planning often treats them as separate domains. Fuel dependency also exposes scale as a liability. Large operations consume massive amounts of energy per day. Their efficiency depends on uninterrupted flow. Small disruptions that a small farm might absorb can cripple a large one. Scale amplifies vulnerability when redundancy is absent. This is why fuel shortages disproportionately affect highly mechanized regions. The systems designed to produce abundance quickly are the least tolerant of interruption. Speed requires power. Power requires continuity. When energy systems fail, agriculture becomes visible not as an industry, but as an emergency. Governments scramble to protect supply. Rationing discussions emerge, but by the time these measures are considered, critical field operations may already be lost. The lesson is uncomfortable but clear. Food does not come first. Fuel does. Any food system that ignores this hierarchy is planning for success, not survival. In the next section, we move from immediate energy failure to a slower, more deceptive disruption. Fertilizers. Because when nutrients disappear, the damage hides until it cannot be reversed. Unlike fuel, fertilizer failures do not announce themselves immediately. There is no idle machinery, no silent engines, no visible standstill. Fields remain green, crops emerge. From the outside, everything appears functional. This is what makes nutrient disruption one of the most dangerous failures in modern agriculture. The damage is delayed, cumulative, and often irreversible by the time it becomes visible. Modern yield models are built around precision timing. Nutrients are not applied when convenient. They are applied when plants can absorb them most efficiently. Miss that window and the season is compromised. Apply too early and nutrients volatilize or leach away. Apply too late and the plant has already passed the stage where yield potential is determined. Fertilizers are not interchangeable inputs. Nitrogen, phosphorus, and potassium each play specific roles at specific moments. Disrupt one element of that balance and the entire system degrades. The plant may survive, but survival is not the goal. Yield is. When fertilizer supply chains break, farmers face decisions with no good options. Do they reduce rates and spread limited supply across more hectares, accepting lower yields everywhere? Or do they concentrate inputs on fewer fields and abandon the rest? Both choices lock in loss. The only variable is where that loss will appear. What makes fertilizer disruption particularly deceptive is that its effects are invisible to non-producers. Crops still grow, fields still look productive. The crisis is hidden in cellular processes, root development, and grain fill that has not yet occurred. By the time the yield monitor records the loss, the cause is months in the past. This delay disconnects cause and effect. Public narratives often attribute reduced harvests to weather anomalies or farmer mismanagement. The real issue may have been a shipment delay during planting season that never made headlines. Fertilizer production itself is deeply energy dependent. Nitrogen fertilizers rely heavily on natural gas. When energy systems are stressed, fertilizer output drops long before farms feel the impact directly. This creates a second-order dependency. Even if fuel is restored quickly, fertilizer shortages may persist through an entire season. Storage offers limited protection. Many fertilizers degrade, absorb moisture, or become unsafe when stored improperly. Large stockpiles require infrastructure that many farms do not maintain because constant supply has made it unnecessary. Efficiency once again replaces resilience. In highly optimized systems, fertilizer inventories are intentionally minimal. Cash flow models discourage tying capital into stored inputs. This works when logistics are stable. When they are not, farms discover that savings from efficiency are trivial compared to losses from disruption. Timing pressure also eliminates flexibility. Biological processes do not wait for markets to stabilize. A missed nutrient application cannot be recovered with double rates later. Yield potential is defined early, and once lost, it cannot be reclaimed. This creates a form of agricultural debt. The season appears normal, but the outcome is already compromised. When harvest arrives, the system pays for decisions it was forced to make under constraint. Fertilizer disruption also amplifies inequality between farms. Operations with pre-purchased inventory or access to alternative sources maintain yields. Others fall behind permanently. Recovery is uneven, and consolidation accelerates. The lesson is subtle but critical. Fertilizer failure does not look like failure until it is too late to respond. Systems that ignore timing are systems designed to fail quietly. In the next section, we move from physical inputs to invisible ones. Data, GPS, and digital infrastructure. Because when information fails, precision collapses into approximation. Precision agriculture is built on an assumption that rarely gets tested: that information will always be available, accurate, and continuous. Modern farms rely on positioning signals, correction services, cloud-based platforms, digital prescriptions, and real-time analytics to operate at scale. When these systems function, efficiency appears effortless. When they do not, precision collapses instantly. Unlike fuel or fertilizer, data failures do not stop machinery outright. Tractors still move, planters still plant, sprayers still spray. The danger is more subtle. Operations continue, but without guidance. Decisions revert from optimized to approximate. Errors multiply quietly across thousands of hectares. GPS accuracy is not a given. High-precision agriculture depends on correction signals that can degrade or disappear during systemic disruption. Without them, guidance drifts. Overlaps increase. Skips appear. Input application becomes uneven. Individually, these errors seem minor. At scale, they represent lost yield, wasted inputs, and irreversible inefficiency. Digital prescriptions are another hidden dependency. Variable rate planting, fertilization, and spraying assume access to maps generated from historical data and predictive models. When servers are unreachable or licenses lapse due to payment or connectivity issues, operators default to static rates. The system falls back to averages designed for no one in particular. This regression exposes a structural truth. Many modern farms no longer retain the internal knowledge required to operate optimally without digital assistance. Agronomic intuition has been partially externalized to software. When that software is unavailable, decision-making slows or degrades. Data dependence also concentrates risk. Large operations manage complexity through centralized digital platforms. A single point of failure can affect thousands of machines and operators simultaneously. Smaller farms may be less efficient, but they are often less digitally fragile. Connectivity failures also disrupt coordination. Harvest timing, transport scheduling, storage allocation, and labor management all rely on real-time communication. When systems fragment, delays cascade. Grain waits, equipment queues grow, biological processes continue while digital synchronization breaks down. There is also a psychological dimension to digital failure. Operators trained to trust automated guidance experience hesitation when systems go dark. Manual operation feels slower and riskier. Confidence drops, even when the machinery itself is capable. Technology was adopted to reduce variability. Ironically, its absence increases it beyond what traditional systems experienced. Precision agriculture does not degrade gracefully. It fails sharply because it removed the buffers that once compensated for uncertainty. This does not mean digital systems are a mistake. It means they were deployed without sufficient consideration for failure modes. Backup data access, local processing, offline capability, and manual override training are often neglected because disruption is treated as unlikely. When information systems fail, agriculture loses its edge not in production capacity, but in coordination. The field becomes disconnected from the system that gives its actions meaning. In the next section, we examine the layer that connects all others. Logistics, because even when crops are grown successfully, food does not exist until it moves. In modern agriculture, production is only half the system. The other half is movement. Crops become food only when logistics complete the chain. Storage, transport, scheduling, and coordination determine whether a successful harvest feeds people or decays in place. When logistics fail, abundance turns into waste. Logistics is often treated as a downstream concern, something to be optimized after production decisions are made. In reality, logistics defines the limits of production itself. A farmer may grow a record crop, but without reliable transport and storage, that achievement has no value. Disruption exposes this immediately. Grain elevators fill faster than expected. Trucks arrive late or not at all. Fuel shortages prioritize emergency transport over agricultural movement. Roads become bottlenecks. Ports slow. The system clogs. Unlike field operations, logistics failures compound rapidly. A delayed truck creates a queue. A full silo halts harvest. A missed shipping window cascades into weeks of backlog. Each delay increases loss through spoilage, quality degradation, and financial penalties. Storage is not a neutral buffer. It requires energy, monitoring, and maintenance. Temperature control, aeration, pest management. When power is unstable or labor is constrained, stored crops deteriorate. The illusion that storage buys unlimited time collapses quickly. Timing pressure intensifies at harvest. Crops reach maturity together. Moisture levels rise or fall daily. Weather windows narrow. Logistics must perform under peak load precisely when systems are most stressed. There is no margin. Highly centralized logistics amplify risk. When many producers rely on the same facilities, failure becomes synchronized. A single elevator outage affects entire regions. Decentralized systems are less efficient, but more forgiving. Financial exposure also concentrates in logistics. Contracts specify delivery dates and quality thresholds. When disruptions prevent fulfillment, penalties apply regardless of cause. Farmers absorb losses created far from their fields. Transport distance, once abstracted by cheap fuel and stable infrastructure, becomes decisive again. Farms closer to processing and storage survive disruptions more easily. Geography reasserts itself. The critical insight is simple. The most important field in modern agriculture is not soil. It is logistics. When that field is neglected, no amount of agronomic excellence can compensate. In the next section, we examine why some farms endure these failures while others collapse. Resilience is not accidental, it is designed. When systemic disruption hits, outcomes diverge rapidly. Some farms absorb the shock, adjust operations, and continue producing at reduced but viable levels. Others collapse within a single season. This divergence is often misattributed to luck, size, or management talent. In reality, it is structural. Resilient farms are not defined by ideology or nostalgia. They are defined by design choices made long before disruption occurred. These choices rarely maximize short-term efficiency. Instead, they preserve optionality. Input diversification is the first divider. Farms that rely on a single supplier for seed, fertilizer, fuel, or services expose themselves to single-point failure. Those with multiple sourcing paths accept higher routine costs in exchange for continuity under stress. When one channel fails, another partially compensates. On-farm storage is another critical factor. Fuel tanks, fertilizer sheds, spare parts inventories. These assets appear idle during stable periods, which makes them easy to cut during optimization cycles. During disruption, they become lifelines. Storage converts time into flexibility. Decision autonomy also matters. Farms that retain agronomic and operational knowledge internally adapt faster when external systems fail. They can operate machinery manually. They can adjust rates without digital prescriptions. They can improvise without waiting for permission from platforms or advisors. Scale plays a complex role. Large operations benefit from capital access and bargaining power, but they also carry massive daily burn rates. When systems fail, their fixed costs become liabilities. Smaller farms often have lower throughput but greater agility. Neither model guarantees survival. Design does. Resilient farms also simplify where possible. Fewer crop types, fewer specialized inputs, equipment that can perform multiple tasks. Simplicity reduces exposure. Financial structure is equally important. Low leverage provides breathing room when revenue is delayed or reduced. Highly optimized financial models assume continuity. When that assumption breaks, debt accelerates failure. Perhaps the most overlooked factor is mindset. Resilient farms plan for disruption without expecting it. They treat stability as temporary. This perspective shapes investment decisions subtly but decisively. The pattern is consistent across regions and systems. Farms that survive disruption do not do everything better. They do fewer things with more tolerance for failure. In the next section, we examine the role of technology in this divide. Because the right tools can amplify resilience, while the wrong ones magnify fragility. Technology is often framed as a promise of control. In agriculture, that framing is incomplete. The most valuable role of FarmTech is not maximizing yield in perfect seasons. It is reducing loss when conditions degrade. When disruption occurs, technology either acts as a buffer or becomes an amplifier of failure. Resilient FarmTech is designed around degradation, not perfection. Systems that assume continuous connectivity, uninterrupted power, and stable supply chains perform well only while those assumptions hold. When they do not, the absence of fallback modes turns sophistication into fragility. The most effective technologies in disrupted environments share common traits. They function offline. They store data locally. They allow manual override without disabling the system. They prioritize situational awareness over optimization. Monitoring systems are a prime example. Sensors that track soil moisture, fuel levels, storage conditions, and equipment status provide early warning rather than late diagnosis. Knowing what is failing first allows farms to allocate scarce resources more intelligently. Predictive models also shift in purpose under stress. Instead of optimizing yield, they are used to model loss scenarios. Which fields should receive limited fertilizer? Which operations must be prioritized if fuel is rationed? FarmTech becomes a decision triage tool. Automation, when applied carefully, reduces labor dependence during instability. However, automation that cannot be operated manually introduces risk. Resilient automation simplifies human intervention rather than replacing it entirely. Data ownership becomes critical during disruption. Farms that control their data retain continuity when platforms fail. Those dependent on external servers lose visibility at the worst possible moment. The key distinction is philosophical. Fragile technology asks the system to remain stable. Resilient technology assumes instability and adapts. FarmTech does not eliminate risk. It compresses recovery time. It transforms chaos into constrained damage. When evaluated through this lens, technology investment decisions change. In the next section, we step back and examine the broader system these farms operate within. Because food systems do not fail in isolation, their failure reshapes societies. Food systems are rarely discussed until they fail. When they function, they disappear into routine. Supermarkets are stocked. Prices fluctuate within familiar ranges. Meals arrive on time. This invisibility is not accidental. It is the result of systems designed to operate quietly, efficiently, and without drawing attention. But invisibility has a cost. Systems that are not seen are not questioned. Their assumptions remain untested. Their dependencies remain hidden. When disruption exposes them, the shock feels sudden, even though the fragility was always present. Modern societies treat food as a commodity rather than infrastructure. Roads, power grids, and water systems are recognized as critical. Food systems are assumed to be self-sustaining. This assumption collapses quickly under stress. When food systems falter, social stability erodes. Prices rise before shortages appear. Trust weakens before shelves empty. Panic is not caused by hunger alone. It is caused by uncertainty. People do not fear scarcity as much as they fear unpredictability. Agriculture sits upstream of this reaction, absorbing pressure long before it becomes visible. Farmers experience disruption as operational failure. Consumers experience it as emotional shock. The gap between these experiences hides responsibility and delays response. Policy responses often arrive late because the system lacks clear signals. There is no single alarm that announces food system failure. Instead, there are thousands of small breakdowns spread across fields, warehouses, and transport routes. This distributed failure makes accountability difficult. No single actor causes collapse. No single fix restores stability. The system fails because it was never designed to be stressed. Understanding food as infrastructure changes priorities. It shifts focus from output to continuity, from efficiency to tolerance, from growth to durability. In the final section, we bring these threads together. Because the lesson of systemic disruption is not about fear. It is about design. Systemic disruption does not negotiate. It does not care about narratives, intentions, or expertise. It reveals what systems are built to endure and what systems are built only to perform. Modern agriculture has achieved extraordinary productivity by optimizing every layer of production. In doing so, it often traded resilience for speed. This trade was invisible while systems remained stable. Under disruption, it becomes decisive. The farms and food systems that survive are not those that deny complexity, nor those that chase maximal efficiency. They are those that assume failure is possible and plan accordingly. Resilience is not resistance to change. It is the capacity to absorb shock without losing function. It requires redundancy, flexibility, and humility. The future of agriculture will not be decided by larger machines or more data alone. It will be decided by whether systems are designed to degrade gracefully rather than collapse abruptly. Food does not fail because people argue. It fails because dependencies break. If there is a single lesson to take from disruption, it is this. Systems that feed societies must be built not for perfection, but for survival. Because when systems fail, farms feel it first. And when farms fail, everything else follows.